Welcome to this deep meeting talk at City, Academia Sinica. My name is Jiawei Liao, a Ph.D. candidate in computer science at National Taiwan University. Today's talk is titled Towards One-Step Diffusion and Flow. From consistency model to flow map models. We will trace the evolution of fast generative models that aim to reduce the multi-step sampling bottleneck of diffusion models down to a single neural network evaluation. Here is what we will cover today. First, we will briefly recap the foundations of diffusion models and flow matching. Then we will dive into consistency models, which formulate a direct one-step mapping from noise to data. Finally, we will look at flow map models, specifically consistency trajectory models and mean flow, which generalize this idea to learn arbitrary jumps along the probability flow trajectory. The key researchers whose work we will discuss include Yang Song from OpenAI, Xiaoxin Jesse Lai from Sony AI, and Kaiming He from MIT. Let us start with a quick review of generative model learning. The goal is to model the distribution of natural data, for example, images of cats. We observe many different cat images, each looking different but all belonging to the same category of natural, realistic data. The challenge is to build a model that can generate new images that look equally natural and realistic, without simply copying the training data. More formally, we model these cat images as samples drawn from a data distribution. Each image corresponds to a point, and the collection of all real cat images forms a structured distribution in high-dimensional pixel space. The model must learn to approximate this distribution so that new samples it generates also lie within the same structured region. In most generative models, we transform samples from the data distribution into a simple noise distribution, and then learn to reverse this process. The figure shows multiple arrows from the data distribution on the left to the noise distribution on the right. Each arrow represents a sample being progressively corrupted into noise. The generative model must learn to reverse these arrows, mapping noise samples back to realistic data. The ideal scenario is a direct, single-step mapping. Given a sample from the noise distribution, we apply one transformation and immediately land on a realistic data sample. This is the dream of one-step generative modeling, and it is the core motivation for the methods we will discuss today. This is the fundamental goal of generative modeling. Building a bridge between the noise distribution and the data distribution. The key question is, how do we build this bridge efficiently? Multi-step diffusion models build it gradually, one small step at a time. One-step models try to cross the entire gap in a single leap. Before diving into one-step models, let me briefly revisit what diffusion models do. The forward process adds noise step by step, corrupting data into pure Gaussian noise. The reverse process progressively denoises, recovering data from noise. The standard multi-step approach is very effective but slow at inference time because it requires many sequential model evaluations. Formalize the diffusion process, we think of each sample as a point evolving along a stochastic trajectory over time. Starting from clean data at time 0, the forward process takes the sample on a random walk through high-dimensional space, ending at pure Gaussian noise at time t. The marginal distribution at each time slice shifts smoothly from the data distribution to the noise distribution. As we observe this stochastic process, the key question is, how do we describe it mathematically in a way that enables efficient generation? The answer is to model the evolution of the marginal distributions over time using differential equations. The score-based diffusion model framework by Yang Song and colleagues formalizes this using stochastic differential equations. The forward SDE corrupts data by adding noise according to a drift term F and a diffusion term G times a Wiener process. The reverse process has two equivalent forms. The reverse SDE, which is stochastic, involves the learned score function S theta. The reverse ODE, which is deterministic, uses half the score function weight. Crucially, both produce the same family of marginal distributions from time 0 to t. In practice, we can use either for sampling. Let us compare score-based diffusion models and flow matching side by side. For score-based diffusion, the velocity field in the reverse ODE is f-1/2 g squared times s theta, and training minimizes the score matching loss, the expected squared difference between s theta and the true score. For flow matching, we directly learn the velocity field v theta that drives samples along straight paths from noise to data. The flow matching loss is simpler. It minimizes the expected squared difference between the predicted velocity and the ground truth velocity along the interpolation path. Both approaches define a probability flow ode, but flow matching uses a simpler, more direct parameterization. Now let us turn to consistency models, introduced by Yang Song and colleagues at ICML 2023. The key idea is to learn a consistency function f theta that maps any noisy point on the probability flow ode trajectory directly to the clean data x0 at the origin. Formally, f theta of xt and t equals x0 for all t in the range 0 to t, and f theta of x0 and 0 equals x0, the boundary condition. Any 2 points on the same trajectory must map to the same clean image. This property, called self-consistency, is what enables one-step generation. To train a consistency model, we use pairs of adjacent points on the probability flow trajectory. Given a noisy sample x at tn, we take a small Euler step to get an approximate x at tn-1. We then require the consistency function to output the same x0 from both inputs. The CM loss penalizes the difference between f theta of x at tn and tn, and f of the stop gradient of x at tn-1 and tn-1, where the stop gradient target uses an exponential moving average of the model weights. This formulation avoids backpropagating through the ode solver. Consistency models can be trained in 2 modes. Consistency distillation uses a pre-trained diffusion or flow model to compute the velocity field. For diffusion, the velocity is negative t times the score s phi. For flow, the velocity is v phi from the pre-trained flow network. In both cases, the Euler step provides pseudo-targets on the probability flow. However, the paper highlights a key limitation: slow convergence, because adjacent Euler steps are very close together, giving weak training signal. This motivates more powerful flow map approaches. Sampling with consistency models is elegant. The model can generate a sample in a single step by applying f theta directly to noise at time t. For better quality, we can use multi-step refinement. After the first prediction x0, we add noise to get x at tn-1, then apply f theta again to refine the estimate. Each additional step improves quality while still requiring far fewer function evaluations than standard diffusion. Here are experimental results from the CM paper. On Cipher-10 and ImageNet 64x64, consistency models achieve competitive fit scores compared to GAN-based models and diffusion-based distillation methods, while requiring only 1 or 2 function evaluations at sampling time. The results confirm that the consistency framework enables fast and high-quality generation without full multi-step diffusion inference. Now let us generalize the consistency idea. Instead of mapping any noisy point directly to x0, what if we learn to jump between any 2 arbitrary time steps on the probability flow? This is the concept of a flow map. Given x at time t, the flow map psi from t to s applied to xt gives us the corresponding x at time s along the same trajectory. Consistency models are a special case where s equals 0. A general flow map model can learn any jumps along the trajectory. Consistency Trajectory Models, or CTM, introduced by Kim and colleagues at ICLR 2024, implement this idea. The model G theta takes xt, the start time t, and the end time s as inputs, and produces xs, the position on the probability flow at the target time. For training, we sample triples of time steps t, t prime, and s, with t greater than t prime. We first take a small Euler step from xt to get x at t prime, then apply g theta from t prime to s. The loss enforces that 2 ways of reaching s, directly from t, or via an intermediate t prime, produce the same result. The target uses stop gradient to stabilize training. CTM introduces 3 complementary training losses. The CTM loss enforces trajectory consistency. The DM loss provides a local training signal. When the start and end times t and s are very close, the CTM loss gradient becomes weak because the jump is small and provides little learning signal. Adding the diffusion model loss, which predicts the velocity field locally, provides a stronger gradient in this regime and stabilizes optimization. The GAN loss adds an adversarial discriminator term to prevent overly smooth outputs, encouraging sharper and more realistic samples. The total loss combines all 3 with learnable weights. CTM achieves strong results on Cipher-10 and ImageNet benchmarks, often outperforming consistency models and matching or exceeding GAN-based methods in single-step generation. However, the training pipeline is complex. It requires a pre-trained diffusion model as a teacher, careful tuning of multiple loss weights, and an adversarial discriminator. This raises the question: can we design a simpler and more efficient training strategy that achieves equally good results? This brings us to MeanFlow, a recent approach that rethinks the flow map parameterization from scratch. The key insight is about what the flow map actually approximates. We want to compute xs from xt by integrating the velocity field from t to s. With just one neural network evaluation, we cannot compute this integral exactly. Euler's method gives only a first-order approximation with error of order s minus t squared. Instead, MeanFlow defines u theta as the average velocity over the interval from t to s, that is, 1 over s minus t, times the integral of the true velocity v from t to s. This average velocity, when multiplied by the time interval s minus t, gives a much better estimate of the displacement from xt to xs. The key mathematical identity that makes MeanFlow trainable is the MeanFlow identity. By differentiating the definition of u with respect to t, we obtain u of xt, t, s equals v of xt, t plus the quantity s minus t times the time derivative of u of xt, t, s. This connects the average velocity u to the instantaneous velocity v and the rate of change of u along the trajectory. The left side is what we want to model. The right side can be computed from the model's own output, enabling a self-consistent training target without needing a pre-trained teacher model. To compute the time derivative of u with respect to t, we apply the chain rule, treating xt as itself evolving according to the velocity field. The total time derivative of u decomposes into a spatial Jacobian term, a partial time derivative term, and a term from the dependence on s, but since s is fixed, its contribution is 0. The result is the Jacobian vector product of the gradient of u with the vector vt, 1, 0. This Jacobian vector product can be computed efficiently using forward mode automatic differentiation, making the full training target tractable. Putting it together, the MeanFlow training objective minimizes the expected squared difference between u theta of xt, t, s and the target u target. The target is computed by substituting the stop gradient version of u into the MeanFlow identity. U target equals vt plus s minus t times the Jacobian vector product of the stop gradient u with v, 1, 0. The stop gradient prevents gradient from flowing through the target, stabilizing training. This formulation is self-contained. It requires only a flow matching model as a starting point and no adversarial training or pre-trained teacher. Sampling with MeanFlow is straightforward. In multi-step sampling, at each step we evaluate u theta at the current position x at ti plus 1, with start time ti plus 1 and end time ti, and take a step of size ti minus ti plus 1. In one-step sampling, we simply evaluate u theta with x-1 at noise time 1, start time 1, and end time 0, and compute x0 as x-1 plus u theta times the interval length of 1. This single evaluation gives a clean sample directly from noise. MeanFlow achieves state-of-the-art results on ImageNet 256 by 256 among one-step and few-step generation methods without pre-training from a teacher model. In the one-step setting without classifier-free guidance, MeanFlow outperforms consistency models and matches or exceeds CTM-based methods. With multi-step sampling, MeanFlow XL with 2 steps achieves and fit around 3.43, competitive with much more complex pipelines. These results demonstrate that integral-based velocity averaging is a powerful and simple technique for one-step generative modeling. Let us summarize what we have covered. Consistency models formulate diffusion generation as a one-step mapping problem, supporting both distillation from pre-trained teachers and direct training from scratch. Consistency trajectory models extend this by learning the full flow map along the probability flow trajectory, using multiple loss terms, including a DM loss and GAN loss, to improve generation quality. MeanFlow introduces a principled reformulation using the average velocity integral, with a mathematically elegant self-consistent training target that avoids complex multi-loss pipelines, achieving strong one-step generation results. There is a rich ecosystem of follow-up work in both directions. On the consistency model side, notable successors include improved consistency training, easy consistency model, and simple stable scalable consistency models. On the flow maps side, the highlighted papers from today, consistency trajectory models and mean flow, have inspired further variants such as shortcut model, improved mean flow, and consistency mid-training. If you want to go deeper, these papers are great starting points. For further reading, I strongly recommend the book-length tutorial The Principles of Diffusion Models. From Origins to Advances by Chia-Shin Jesse Lai and colleagues, including Yang Song, Dongjin Kim, Yuki Mitsufuji, and Stefano Urman. Jesse's tutorials and insights have greatly inspired the structure and content of today's presentation. Thank you very much for your attention. I hope this talk has given you a clear picture of the journey from multi-step diffusion models to efficient one-step generation, and how consistency models, consistency trajectory models, and mean flow each contribute to making fast, high-quality generative modeling a practical reality. Please feel free to reach out if you have any questions. Thank you again for joining this deep meeting session. The slides and references will be made available for further study. If you are interested in implementing these methods or diving into the theory, the recommended reading and follow-up papers listed in the previous slides are excellent starting points. I look forward to continued discussions on pushing the boundaries of efficient generative models.